Okay, so we'll go back to another video. So here we have a improper integral of our integrand is x times e to the negative x squared divided by 1 plus 2 times x to the power 4th. So everything in combination in the process we'll be dealing with is there's going to be a lot of things. So I'm sure that you're probably thinking, will there be a u-sub involved? And yes, there will be. But there's also other things that are interesting that's going to be used in the process. Specifically, we'll be using the Laplace transform. Not only that, we'll be utilizing its inverse Laplace transform as well. And throughout that process, we can actually reduce down to some point of a trigonometric function and beyond, and eventually to that point that we'll actually be utilizing some special trigonometric integrals to simplify the answer as it is. So what those trigonometric integrals are, well, I'll leave that for you to leave that in your imagination, or if you want to skip forward to the video, you can. But with that out of the way, it's pretty simple. From there, we'll be utilizing those methods. So why don't we actually just jump right in? So first, let's utilize a u-substitution. We'll let u equals x squared. And so we'll substitute this from whatever from our Gaussian function that's being multiplied through. Then I have that du is equal to just 2x and then dx. So with that in mind, I can actually just divide the 2 to both sides, and I get a factor of 1/2 that I can put outside, and then the x will cancel out from that differential. Then don't forget, we also have to make sure we have to substitute everything in terms of in terms of the world of u. So what we have so far is capital I, which is going to be our given integral we're going to integrate to find the value of. We have that's 1/2. Then multiply, so change our bounds. Luckily, it's still going to stay the same, thankfully. So from 0 to infinity. Then I have e, then to the negative u, and then divided by, so 1 and then plus, so I have a x to the power 4 where we said the u is equal to x squared. So that's going to be 2 times u squared and then du. Okay, so with this in mind, this might be a little bit difficult to proceed forward with this. So there's a reason why I said we'll be using both the Laplace transform and its inverse transform. So let's actually write down what the Laplace transform specifically says. So our Laplace transform is actually written as follows. So we have this cursive L in respect to the function, or rather the variable for u, of a function of u in terms of our variable for s is simply just going to equal to the integral from 0 to infinity of e to the negative s times u, and then times our function fu, and then du. And another thing to note that we're going to be using a nice little property such that if we have a product of the two functions specifically for f of u and g of u, so the integral from 0 to infinity of f of u times g of u du, we're going to have that, this is the same thing written as the integral from 0 to infinity of our Laplace transform for f of u, and then for the variable s, and then multiply by its inverse transform. So instead with the variable for g of u and then for the variable s, but that's also converted to our integral isn't the variable in the world of s. Okay, so with this in mind, so we have to choose in this situation what are f of u and g of u. We're either going to take the Laplace transform and respectively take its inverse transform. So why don't we actually transform our following function? We'll take our Laplace transform of e to the negative u. So with this in mind, so by definition, we just utilize that. So f of u is going to be e to the negative u, and in respect to s. In other words, that's the same thing written as our integral in definition up here is 0 to infinity of e to the power s times u, and then multiplied by e to the negative u, then du. This is actually very simple to compute, so I'll actually just skip ahead, and we'll have that this is actually going to equal to just 1 divided by 1 plus s. So what is our transform, our inverse transform we're going to be using? So why don't we actually now utilize, so our inverse, we'll use the function 1 divided by 1 plus 2u. But first, I think it's good to mention that first, that if I actually take the Laplace transform specifically of our sine function for a constant, so just to keep yourself a reminder that in the variable for u, so our function sine of u, or sine of a times u, we know that the generality of finding that closed form for the Laplace transform is equal to a divided by a plus s squared. So of course that utilizes to say that the inverse Laplace transform for, and this is for the variable s, of a divided by a plus s squared, or is supposed to be a square, so that's an a square over here as well. A square and n plus s square in the variable for u is simply just going to equal to just sine times a times u. So we see that if I plug 1 divided by 1 plus 2u, so therefore implying that after all utilizing this sort of definition, so then the inverse transform of 1 divided by 1 plus 2u square. So let me actually simplify things a little further before we actually take its transform rather than actually just simply plugging it in. So what we have is that I can actually factor out a 1 divided by the square root of 2 from over here. So that means I have 1 divided by square root of 2, then I multiply, so over here it's going to be 1 divided by the square root of 2. That's just the numerator, and under the denominator I have 1/2 and then plus u square. Okay, we close that off, and then we can simplify it further such that this is just a constant, so I'll factor that out. So I have 1 divided by the square root of 2 multiplied by the inverse transform, Laplace transform of now 1 divided by the square root of 2, and then divided by 1/2 plus u square, and then for the variable s. And so therefore, if we just plug in everything that utilizes that same definition from over here, this is simply just going to equal to just 1 divided by the square root of 2, and then multiplied by sine of s divided by the square root of 2. Okay. And so with everything that we just written down, so now we can actually come down to this following simplification for capital I that we're being given to integrate. Therefore, I have that our capital I so far is going to be written as 1 divided by 2 times the square root of 2. So that's simply just not only factoring out the 1 divided by square root of 2 and factoring out that outside, and then that's 1/2 still outside there, of course. And so the integral from 0 to infinity, and now our variable is going to be in terms of s. So now I have the sine of the square root of 2 divided by, or excuse me, s divided by the square root of 2, and then divided by 1 plus s, and then ds. Where do we go from here? Why don't we actually now take another u-substitution? We'll let our variable t be the new variable that we'll be substituting. We'll let t equals 1 plus s. And so that means I have that dt is going to equal to just ds. And then so now that just comes down to our simplification for our u-sub. So we have 1 divided by 2 times the square root of 2. And then so we actually plug in our bound. So I have infinity on the top so far. But if I plug in 0, I have 1 on the lower bound. And so what we have is, so I gotta make sure we write this in terms of s, so just get this by itself. That means that I have t minus 1. And then what I'm gonna do is, I'm actually gonna split this into the difference of the fractions instead of combining into one fraction. You'll see why I actually do this. So I have sine, and then I have t divided by the square root of 2, then subtract with 1 divided by the square root of 2 as our input, and then all divided by t, and then dt. Now, that leaves the question on how are we supposed to integrate this? Well, we don't actually do any sort of integrating just yet. Instead, what we're going to do is we're actually going to utilize a nice trigonometric identity for the difference of its input for sine, which says that for some sine of a minus b for the difference of the value is the same thing is equal to sine of a multiplied by cosine of b, and then subtract cosine of a multiplied by sine of b. So that's our trigonometric property that we'll be utilizing to substitute the following of our numerator. So continuing forward, so that means I'm actually going to continue from here. So sine of t divided by the square root of 2, then subtract 1 divided by the square root of 2. So basically, in other words, that's going to be the same thing written. So I'll put this over here. It's going to be equal to sine times t divided by the square root of 2 multiplied by cosine of 1 divided by the square root of 2, then subtract cosine of t divided by the square root of 2 multiplied by sine of 1 divided by the square root of 2. And thankfully, these two are actually our constants, because afterwards, once we actually put everything back into over here, there's some things we can actually factor out of that integral. So that means continuing on. So I have that our substitution I, or capital I as our new rewritten integral, is going to be written as follows. And so also keep in mind that we're also putting in the, the linearity and the distributions for our new substitution of our sine, or rewritten sine identity. So what we have now rewritten is going to be 1 divided by 2 times the square root of 2 multiplied by cosine of 1 divided by the square root of 2. That's the constant, so I can just factor out the integral. So I'll multiply with the integral of 1 to infinity of sine multiplied by t divided by the square root of 2, and then divided by t, then dt. Then we actually can now subtract this with now 1 divided by 2 times the square root of 2. Factor that out, so I have sine of 1 divided by the square root of 2, then multiply by our integral from 1 to infinity of sine, then, well actually this is supposed to be now the cosine because we switched for sine and then now cosine. So cosine of t divided by the square root of 2, and then divided by t, then dt. So what we have here, I'm actually going to box this because just to reiterate, because moving on, we're actually going to erase all this stuff to continue forward with the work. So this is what we have written so far. So now with this in mind, let's actually get rid of everything I've written on the board and then continue on from here. Okay, so from the last scene so far, last clip, that we have come down to the simplification that our given integral, we reduce this down to this following expression over here. So now what's left is we have to tackle these two integrals. So there's some things that we need to pay attention carefully. So why don't we actually first start off with our sine of t divided by square root of 2 divided by t integrand. So this is actually interesting because the way you want to do this is we're actually going to break up its bounds. So we're going to note that the integral of our given over here for this integral specifically, so sine of t divided by the square root of t and then divided by t, or square root of 2, excuse me, and then divided by t and then dt, I can actually break out our bounds. So I have that we can write this as from 0 to infinity of our same integrand, and then so divided by t, then dt. Then we can subtract a piece of that. So that means I can subtract from the integral from 0 to 1 of our integrand as written. So sine divided by, or sine of t divided by square root of 2, and then divided by t, then dt. Then from here, we actually want to perform a nice little u sum. We're gonna let u be t divided by the square root of 2. So that means du is simply just gonna equal to 1 divided by the square root of 2, and then dt. So with this in mind, so now let's actually perform our new rewritten integral. So what we have that over here is going to be written. So we have our new integral for the new bounds for u. I plug in 0, that's going to be 0. And if I plug in infinity, that's still going to be infinity. So thankfully, no bounds have changed, thankfully. So I have sine of, so replace this of sine of u. And then on the bottom, what I have is t. So I solve this by t by itself. So I have square root of 2 times u. And then if I multiply our du differential for the new substitution, then that square root of 2 is actually going to cancel from the numerator and denominator from the whole denominator, which reduces down to simply just u and then du. Okay, so now let's actually perform the same thing for this one. So this is actually just going to be the same thing essentially. So that means, so 0 is going to be on the bottom, and then on our top for our upper bound, if I plug in 1, that means I have 1 divided by the square root of 2 for our upper bound. And then I have, now it's just going to be the same thing. So sine of u, and then divided by u, then du. Okay, so that in mind, you're going to notice that this is a very interesting simplification that we can come down to, such that our middle integral we're dealing with, this is actually the well-known value of the Dirichlet integral. Specifically, it comes down to pi divided by 2. And then for our value over here, this is actually a nice integral, a special integral that I mentioned. This is the sine integral. And by definition, this is written as si of x, which is simply just equal to the integral from 0 to x of sine of u divided by u du. So with that definition, that means that I can actually just reduce this down to write in our input for capital SI, so the sine integral evaluated at 1 divided by the square root of 2. So therefore, this is going to equal to pi divided by 2 minus the sine integral evaluated at 1 divided by the square root of 2. Okay, and so with that in mind, so that's actually our new substitution that's actually going to plug in over here. So let me actually, denote this. So pi divided by 2, then minus SI evaluated at 1 divided by the square root of 2 over here. Okay, so that integral's done. Now we got to take care of this integral. So why don't we actually do that? And to continue further with calculating this integral, I'm actually going to put with the negative sign to that as well, just so it leaves everything nice and easy. So the integral we're dealing with in question is all the way at the ends with the negative. So I have negative the integral from 1 to infinity of cosine of t divided by the square root of 2 and then divided by t, then dt. We'll perform our little u sub yet again. So do the same thing just like above. So we'll let u equals t divided by the square root of 2. Then that means du is simply just going to be 1 divided by the square root of 2. And then du, then, or rather, this is supposed to be dt. And so that means if I just plug everything back into over here, so let's see, I have our new bounds. So if I plug in infinity, that's just going to be infinity. Then if I plug in 1, so that means I have 1 divided by the square root of 2 on the bottom, okay? And so with this in mind, then that means, let's see, I plug in cosine, and then that's going to be u, and then divided by, so t, that means I get this by itself, I have square root of 2, u is equal to t, then multiply by the differential substitution over here, those square root of 2's is going to cancel, and so that's just going to simply leave us, and don't forget the minus over here, just left with just u, and then du, and so therefore that this is also in terms of another special integral of a trigonometric integral. Specifically, this is what's known as the cosine integral, which is written in terms of this definition. So this is going to be written as, so in definition in terms, that means it's written as ci of x is going to equal to the negative integral from x to infinity of cosine of u and then du. And so we just plug this value back in, that this is simply just going to equal to just ci, the cosine integral, evaluated at 1 divided by the square root of 2. So with that, we can now put in this substitution over here. So ci of 1 divided by the square root of 2 over here. And then we actually just put everything back together. We actually do plug in here and then perform the distributive method over here. So that means our final answer, capital I, simply is just going to be written as the following. So after evaluating everything that we needed to do. So capital I, therefore, if I distribute all this, everything over here, our final answer is going to be pi divided by 4 times the square root of 2, multiplied by cosine at 1 divided by the square root of 2, and then multiply, or not multiply, subtract, that was done. So minus 1 divided by 2 times the square root of 2, multiplied by cosine of 1 divided by the square root of 2, multiplied by the sine integral evaluated at 1 divided by the square root of 2. And then lastly, we have now, it's a plus of now 1 divided by 2 times the square root of 2, multiplied by sine evaluated at 1 divided by the square root of 2, and then multiplied by the cosine integral evaluated at 1 divided by the square root of 2. So long answer, everything is, this is pretty interesting. And so therefore, this is actually our final answer, box in the pink. So new functions, and that was in the way, that's okay. But everything you see here in the pink, that is our final answer that leads, given from our integral over here, utilizing sine integral, cosine integral. We did a lot of u-sub, and then from earlier, we also applied the Laplace transform and its inverse transform, and which leads to a very long answer, but I think it's also a pretty interesting answer. So yeah, that's pretty cool if you ask me.